Welcome. During our time at NASA Langley, we developed a lesson plan for a project we call Flight Fidelity, Engineering with Practical Mathematics.
We'd first like to introduce ourselves. My name is Lisa Damian, and I teach 11th and 12th graders at Camden Hills Regional High School. I teach honors in AP Physics and Forensics.
And my name is John Fitzgerald, and I teach at Camden Hills as well, grades 9 to 12, geometry, algebra 2, pre-calculus, calculus, and statistics. We'd first like to thank all of the people at NASA Langley Research Center and those who video conferenced with us from off-site for this outstanding opportunity. We'd also like to thank RTI, in particular Olivia Rice, and our den mother, Karen Kelly, for making this possible and keeping us on task. During these past 2 weeks, we met many engineers and scientists, all doing diverse research. We saw many exciting things, from wind tunnel testing to computer simulations of the Mars Science Lab due to launch in November.
Our sincere thanks to Dr. Eric Queen, one of our co-mentors. As you can see, Eric does research in the area of guidance, control, and simulation of aeromaneuvering spacecraft. And it was these ideas that led us to decide to create a lesson on the variable forces acting on an object as it moves through the atmosphere. Eric was especially helpful to us as we gained an understanding of specific impulse and the calculation you use to find the centroid of a non-geometric object. Thank you, Eric.
And thanks also to our other co-mentor, Behzad Raizadeh. Behzad is a project engineer for the Sim-Aero program here at Langley. He helped us with our dynamic thrust modeling and taught us a little bit about the computer programming environments MATLAB and Octave. Both mentors were invaluable resources for checking the accuracy of the content and the processes we present in our lesson plan. And they were lots of fun to work with.
Indeed. So I want to talk first very briefly about the project history. In my honors physics class, I do many engineering design projects. I do at least one a quarter, and they are actually the most favorite parts of my physics curriculum to my students. I hear that all the time. Unfortunately, the pace of the other physics class I teach, AP Physics, is such that I just don't have time to do the engineering projects that I would like to do. On top of that, AP Physics curriculum is much more rich mathematically. It involves much more advanced mathematics, including calculus. And any engineering that I do with them, I would like to integrate calculus instead of algebra-based projects. So I have been searching and searching for an engineering design project that did just that integrated calculus into a hands-on engineering design project. Last year, I was fortunate to begin working with Dr. Paul Vitkowski. He is a professor on sabbatical from Maine Maritime Academy, and he helped me attempt to begin to devise a unit that would bring model rocketry into my classroom, bring model rocketry into my classroom and to begin to use calculus to analyze its motion. So last year I did pilot a program, and in that program my AP students built a model rocket and launched it and did some crude mathematical calculations. This NASA Sim-Aero experience greatly enhanced that project by exposing us to many possible modifications and enhancements of last year's project. Our work has resulted in what we really believe is a rich interdisciplinary lesson plan with the flexibility of greater or lesser mathematical rigor based upon what students you have in your classroom.
Along those lines, let's outline exactly how we decided to structure our lesson plan. We began with what we called the base level lesson, which is suitable for college prep physics students who have covered algebra-based kinematics and Newtonian dynamics. Because of the cognitive complexities of truly understanding the numerical processes that will be used, These students should ideally be in at least their junior year of high school. As was mentioned, the mathematical rigor can be amplified within this project. A description of that is found in the Advanced Physics extension to the base level lesson. Various mathematical extensions have also been developed. Some, all, or none of these extensions can be used in conjunction with the work happening in the physics classroom. Individual math extensions vary in their required levels of math competencies, ranging from geometry to calculus. The learning objectives presented in our lesson plan include concepts related to physics, engineering, mathematics, computer simulations, and error analysis, and they are shown on this screen.
So here is a one-slide overview of the entire project. Students in this project, in the Flight Fidelity project, will be working in teams of 3 students to design a rocket with a 40-gram payload powered by a standard A8 model rocket engine, whose flight path is directly vertical. They then determine all physical characteristics of their rocket, including its drag coefficient, through use of a numerical simulator. Finally, students predict the maximum height their rocket will attain when launched with a different engine having a different thrust profile. So the big question is, why utilize rockets? There are a couple of really important reasons. The first is that this project and the use of solid propellant rockets is really rich in science content. A lot of science that kids are going to be able to apply directly to the curriculum that they've had in my classroom, and that science is deeply embedded in some great mathematical concepts, the engineering design process, and the use of simulators, which is the T technology in STEM. So it hits all of the areas very strongly. A second reason is that a solid rocket, a model rocket, is experiencing dynamic forces, changing forces. This is a step above what a lot of the students do when they do hands-on projects. Most of the time we assume or we look for situations where forces are constant. So this particular project and the use of rockets allows us to approach an advanced analysis of motion. And last but certainly not least, kids like them, even big kids. And if you think about who we are presenting to when we do the AP Physics Capstone Project, these are seniors in their literally last 3 weeks of their high school career. They have been known to have a motivation drop off, and so we really need something especially motivating to reverse that trend. Rocketry does that. So now let's take a more thorough trip through every step of the project and all of its extensions. So phase 1, as you know, is to engage students. To engage students, we are going to first watch a NASA E-clip video called Designing a Capsule for Space. Students will then immediately be allowed to experience the various parts of a rocket because we'll give them a standard stage 1 model rocket to build, something similar to the rocket shown on the screen and SD's Alpha rocket. So they're going to put that Alpha rocket together. It takes about 45 minutes to do that. We don't have an Alpha rocket here, but every rocket sort of has the same parts to it. And the purpose of this engagement is for students to understand what parts of the rocket there are and what they can change. So if you can hold that up. So this is a rocket. Parts of the rocket that the students are going to be able to manipulate include the body. The body is just a cardboard tube. There's nothing special about it. They can come colored, or the kids can color them themselves. They can have different diameters, whatever the student wants. The fins at the end, fins can be made of plastic, pre-molded, and you can buy these. Or they can be made out of balsa wood, and you can buy balsa wood at a local hobby store. At the other end of the rocket, there is the nose cone, and the nose cone also can be pre-bought in different diameters, different shapes, different sizes, and so kids are going to have a lot of options along those lines. They can also make their own nose cones, and this year some of my students did decide to learn how to use a lathe and carve their own nose cones, so that was pretty cool. those really are the parts of the rocket students are going to have the ability to change. Other parts of the rocket you cannot change. They have to be there. So one is the parachute deployment that John is holding right here, the parachute deployment system. You also need an engine, and we will provide the engine. Every group gets the same engine, and you have to mount the engine securely into the back of the rocket. And that's about it. Rockets, although for people who haven't launched them, it may seem complicated or intimidating, it's really very, very simple to do and pretty hard to mess up. So this engaged phase of the lesson, students are just building a rocket to get themselves familiar with the parts. At the end, when they're done building it, we briefly go over those different parts, but sort of nothing beyond that, at least at this stage. The next stage of the lesson is the explore phase. Students begin the explore phase when they're presented with the Fidelity Flight Challenge.
So to review, the criteria for this problem are that the rocket must carry a 40-gram payload, must be able to launch multiple times, must be stable, must fly vertically, and students must define all physical characteristics. The constraints for the problem are that the total mass of the rocket may not exceed 75 grams and that the payload must be secured.
So they have the challenge to design and build a rocket. They're going to, over the course of the next 3 to 4 days, they're going to go through 3 iterations of the engineering design process as defined on the NASA Education Resources page. But before I set them off, I want them thinking about the science, the physics behind it. And so I do very briefly, and only in a conceptual sort of way, talk about the forces that are acting on a rocket that is rising up through the air, because they want it to rise vertically. Those forces, there are only 3 of them. During the propellant burn, there is gravity pulling downward on the rocket, drag force also pulling downward, and the thrust, which is pushing the rocket upward. Once the propellant burns out, the thrust is gone, and now we only have the 2 downward forces that are acting on the rocket. And so the teacher in the lesson prompts the students to consider what other characteristics have an effect on those forces that we put on these diagrams.
For instance, you could ask students to ponder which of these forces would be affected if you increase the body diameter. How would that force or forces be affected? And how would that affect the rocket's motion?
Okay, so students, many of whom we know are naturally competitive, will try to turn the explore part into a competition to get the rocket to go as high as possible. The guidelines of this challenge, however, purposefully challenge students to build a rocket that flies straight up, not a rocket that flies to the highest height. The reason why is because students will be using a numerical simulator to analyze that motion, and the numerical simulator loses accuracy when a rocket veers off to the side. And so it's pretty important for students to design a rocket that will not go in a parabolic curve. From my experience this year, I can tell you that quite often students do design rockets that go in parabolic curves, and there are some tricks that students can access online or through their teacher, if the teacher has experience, to get their rockets to fly straight up instead of off at a curve. And during the design engineering process, that's what we want them to be focused on, straight flight as opposed to the highest flight possible. So as we learned in our 2 weeks here talking about rockets, one of the very important considerations of building a model rocket yourself is that your rocket be stable. And by stable, we mean that it will travel straight and it won't tumble when it is in the air. And part of that is calculating the center of pressure. The center of pressure is a mathematical sort of application, and so it lends itself very well to a treatment from the math teacher.
Okay. A correctly calculated center of pressure is an essential step toward designing a stable rocket. In this math extension, students will calculate the center of pressure using the geometry of the rocket profile In Lisa's physics class, students will find the center of pressure a different way by finding the center of gravity, the centroid, of a silhouette of their rocket. Here is a member of the group, tracing the silhouette using an overhead shadow, cutting it out, and attempting to balance it on a string. However, using accurate geometric measurements along with a scaled drawing of the actual rocket and finding the centroid that way in this extension is designed to mathematically verify the position of the center of pressure found using the silhouette method.
So after students have designed and built a stable rocket, they of course want to launch it. And so that is the next phase here. Students are going to launch. This is a picture, and I'm not sure you can see it on this screen, but it is a picture of a very successful launch my last year's class. You can see it is successful not only because you can really clearly see the smoke trail going practically vertically straight up into the air, but you can also see the rocket in the screen. I was really impressed with my photography skills there, so you're getting such a cool picture. Okay, so to be able to complete the analysis that's coming, the real application of physics, students are going to have to measure the maximum altitude that their rocket does fly. Remember, one of the goals of their project is a vertical launch. Could you show the graphic? Thank you. If the launch is indeed vertical, the maximum height attained can be deduced by applying right triangle trigonometry to the situation. In this case, the maximum height would be equal to the distance from the observer to the launch multiplied by the tangent of the angle recorded by a handheld inclinometer. That measurement's assumption of a vertical launch could lead to error, though, because in reality, rockets often do not go straight up. When this happens, the triangle is no longer a right triangle, so the maximum altitude calculated with the tangent function would be inaccurate. There is a way to eliminate that error, though, which leads nicely into our next mathematics extension.
The basis for this particular extension is trigonometry. Right triangle trig and the law of sines is used. And if you could expand that slide, please. Thanks. This slide, taken from NASA Educational Resources, shows the geometry that would lead to a more accurate measurement. Place two independent observers a fixed distance apart and have them take angular measurements. Two heights are recorded and compared. The math extension, however, asks students to actually develop the trigonometry for this situation rather than just look at a picture.
Okay, so we are now ready, students are now ready to explain the motion of the rocket. Hopefully the rocket is traveling pretty much straight up into the air. To reset their minds on Newtonian physics, students will first watch another NASA ECLIP video, Newton's Laws on board the International Space Station, and that does a great job of reviewing Newton's laws and applying them to rocketry and the International Space Station. Now comes the really heavy physics content, so buckle in as we begin to derive the equation. And if you could expand this slide and keep it up until I ask you to come back to me. Thank you. So, high school physics students have extensive experience deriving appropriate Newton's second law equations from a self-defined force diagram such as this one. The one shown. Thank you, John. Okay, most are familiar with the drag force equation, also shown on the top, and have used it to solve problems at an instant in time where the velocity has been defined. So, the derivation you see here simply reinforces concepts students have prior knowledge of and should not require any inherent instruction. Briefly, students begin with Newton's second law, F equals ma. They account for all forces acting, in this case, drag, thrust, and weight. And when possible, they substitute in the expanded form of the force. Finally, the equation is algebraically rearranged to solve for acceleration. Once the equation is derived, the complexity of the problem can be identified. Newton's second law in this form requires all forces to be constant over time. Think of the motion of a rocket as it rises. The velocity, we know, is constantly changing. If the velocity is constantly changing, the equation for drag force tells us that the drag force must also be constantly changing. Thrust is also changing because of the characteristics of its engine. And to make matters really complex, as if it wasn't complex enough, the mass of the rocket is also changing because the propellant works by pushing mass out of the back of the rocket. Think of Newton's third law. But wait, that's not all. Not only do we have varying constructs, but we also have at least two unknowns in this equation, drag coefficient and acceleration. Students did measure, however, their maximum height of the rocket. And all good physics students know the kinematic equations can be used to get from position to acceleration. However, there is a constraint to using the kinematics equation, and I have them down at the bottom. The second kinematics equation has a constraint of being useful only in situations of constant acceleration motion. We just described the fact that this is not a constant acceleration motion, and so we now have a very complex problem. So, how do we approach solving this problem? Conceptually, instead of looking at the motion from the beginning of the launch to the maximum height, what we're going to ask students to do is to cut that motion into little tiny time intervals. If we then look at just one of those time intervals, we can make a pretty good estimation that in just that little tiny sliver of time, in that 1/100th of a second, we can estimate that the forces remain constant. If the forces remain constant and we know the initial condition, then we're going to be able to use that Newton's law equation to calculate an acceleration that happens over that time period. If we know the acceleration, then we can use the two kinematics equations to calculate the final velocity and the final position at the end of that little time sliver. Fortunately, we do know initial conditions of our rocket. We know that the initial height is 0, and we know that the initial velocity is also 0. So we can cut the motion into little tiny slices, figure out the first slice. When we figure out the first slice, now we have the initial conditions for the second slice. This is an iterative process that we found out engineers use quite often, called Euler's method. Euler's method involves many, many calculations. And in order to do this effectively, engineers use numerical simulators. Numerical simulators can be created using a computer program like Octave or MATLAB, or they can be created on something as simple as a spreadsheet. And so we decided to go with something that our students have experience with, spreadsheets. So let's look at the spreadsheet that can define this motion. And if you could expand that out, please. Thank you. Even expanded, it's sort of hard to see, but you can follow along with me. So here we have it. The goal for students is to go beyond having them simply plug numbers into the spreadsheet as instructed. We want them to have a very deep understanding of exactly how each cell was calculated and why it makes sense to do it that way.
To do that, students' backgrounds should include specific mathematical prerequisites, including analyzing piecewise functions, effectively utilizing sequences, and understanding the iterative processes. To be able to interact with the spreadsheet on a deeper level, students must have a basic understanding of incremental change and Riemann sums as they relate to integration, topics that are usually not covered in our school unit until students progress through a calculus class.
Those distinctions frame the primary difference between our base lesson plan and the advanced physics extension. The base lesson for students with less mathematics experience, in the base lesson for students with less mathematics experience, students will be guided through the structure of the simulator and then will be asked to use a prepared spreadsheet to solve problems. Advanced physics students, though, should have the appropriate level of cognitive and mathematical maturity to self-create the entire spreadsheet after participating in a class discussion of the process. You may notice, by the way, that this simulator, what we're calling a numerical simulator, does not have all of the graphics and bells and frills that many of the commercially available simulators have. One thing we determined pretty quickly here in our 2 weeks at NASA is that real engineers most often use a simulator similar to this, because their goal is just to crunch the data to get some numbers. They wait until the end of the process to create the fancy graphics that go along with the simulator. So this is a nice match with what engineers are doing in the real world. So one of these columns, and I'm not sure if you could go back to the expanded view just for a second, one of these columns, that column right there, asks students to input the thrust that is being exerted by the solid propellant engine. This sets the stage for a wonderful math application that John is going to talk about.
All right, determining the thrust curve. This extension is appropriate for students in pre-calculus and has some elements of calculus in it. Next slide. And if you could expand that, thank you. The values for thrust at certain times can be read off a graph, and if this extension is not used, that's what the students in Lisa's physics class would do. Just read the time and the corresponding thrust. However, the time thrust function of a rocket can also be modeled using piecewise linear functions. A linear function is a sequence. So using those two concepts, a better set of values can be found. In addition, if a very small time increment is desired, a simple computer program can be used to generate a more robust time thrust matrix of values. Whichever method is used, it will generate the thrust values for the numerical simulator.
Once a spreadsheet is set up and they've determined their drag, drag coefficient, students will be asked to elaborate on their new skills by independently. Oh, wait, I'm sorry. Students are elaborating on this lesson by determining their drag coefficient. If they've gotten through the first part of this lesson, determining the drag coefficient is actually a pretty easy thing to do. Looking at the spreadsheet, if students understand this spreadsheet, all they need to do to determine the drag coefficient is to change the value in the drag coefficient cell. There's one cell there that has a drag coefficient, and they're going to be changing that number and looking at the resulting maximum height on the spreadsheet. And they will keep on manipulating that drag coefficient until the height shown on the spreadsheet matches the maximum height measured during their test flight. We want to model the real world here, so students need to be continually reminded of the inherent estimations they are using. Evaluating the effect of these estimations is a valuable process, especially when the computer, I'm not sure you can see it here, but it's generating numbers that look very, very accurate. So it's entirely possible that students believe that because those numbers look accurate, that there is no inherent error in them. To that end, off to another mathematics extension.
Okay. In the basic lesson, the mass of the engine is assumed to degrade linearly, and the mass of the delay and tracking compound is completely ignored. In this extension, students learn a new construct called specific impulse. This defines the thrust force produced per unit mass expelled. The spreadsheet helps them calculate a value for specific impulse for the engine they used, a process that requires the application of a Riemann sum. They then use that value to generate a more accurate profile of the loss of mass of the engine. As a final step, they extend the mass loss to include the mass expelled during the delay and tracking burn. Students are then led through a discussion of the error between the initial crude estimation, the linear degradation of mass, and the more refined method. Okay,
we're finally at the end. There's an evaluation phase. In the evaluation, Students will be testing their understanding of the structure and function of the numerical simulator. We will give the students a different engine. And that different engine will have a different thrust profile, a different mass of propellant, and a different burn time. And so there are several columns and several ways that students need to manipulate that spreadsheet in order to be able to predict a correct maximum height. And so this is really a great way of determining whether they have truly understood what that spreadsheet was doing. Throughout this project, students are evaluated multiple times. In physics, they're going to be graded on the thoroughness of their engineering design journal that they maintain during the explore phase. During the elaborate phase, students will be evaluated on the process they use to calculate the drag coefficient. Points will be awarded both for a correct answer and for the ability to articulate the process used to arrive at that answer. In the evaluate phase, students will again be evaluated on based on accuracy and on articulating their process. Additionally, they will need to write a detailed error analysis for this project.
In the mathematical explorations that we developed for this project, for this lesson plan, there are several worksheets that teachers can use, and each of those worksheets can be graded for accuracy and completion by the student groups learning them, using them. Oh, it is.
Yes, it's you.
Oh, I'm so sorry. What an incredibly cool project this is. A rich interdisciplinary approach to a topic that kids are motivated and inspired by. But there is some cost associated with it, especially startup money. If you're hesitating because of a lack of finances, we've got you covered. The lesson plan includes several sources of easy application, mini grants, $200 up to $200, specific to these fields that you can apply for to help you get started.
Okay, so the folks here asked us to answer some specific questions, and so we are going to very briefly fire through some of these. The first one they asked is how the lesson will be used. And in case we haven't articulated it carefully enough, I will be using this lesson, the base lesson only, in my honors physics course. It will serve as the second quarter engineering project. And as a capstone project in both AP Physics and AP Calculus, because we do share those students, we will use the base lesson plus all of the extensions, and that will happen at the end of next year.
And, oops, is it me? And I'll use the math from this project. Well, we'll certainly coordinate because the two of us do a lot of collaboration throughout the year, but if this project is not used as a capstone project, all of the mathematics that are in the explorations can be used separately. So I would certainly use it during the capstone process. But those individual math, there are 4 explorations, can be actually used as just enrichment activities in a math class that where the level is appropriate, geometry, pre-calculus, or calculus.
Now, we have learned a ton of stuff over the past 2 weeks. It has been so incredibly interesting. And we have been asked how we will use some of what we learned back in our classroom. So we just brainstormed a very brief list of things. Things like kinematics graphs. We've seen a lot of kinematics graphs. I spent a whole quarter on kinematics graphs in my honors level, less time in my AP class, but I'd love to use examples that were real life examples. And so I'm going to be able to bring those back into my classroom.
And the concept of discrete versus continuous function analysis I found very interesting and actually expanded my understanding of those processes, especially the way engineers use that process here. Oftentimes, you know a differential equation, and it's not easy to solve analytically, so you are definitely you definitely have to use numerical techniques, which is probably most often the case, as we have found out. So that's very interesting. Some of the geometry and the trigonometric ideas that you teach for years, but you see new things, you find new things, which is really wonderful. And so those are exciting to take back, and I'll use those. And finally, we learned a little bit about computer programming, which is something that in the past I taught, and I haven't taught it in years, but I learned a little bit more, and I'm quite excited about that, and maybe engaging some of my students in that as well.
And I'll throw one more in as well. I do a unit on thermodynamics, and so a lot of what we learned about heat shield thermodynamics, about conduction rates and rate of heat flow, can bring that as real-life examples back into my classroom. And one really cool thing that we saw was the cryogenic wind tunnel, and we walked under it and we were able to see the structure of the cryogenic wind tunnel. And it turns out when the cryogenic wind tunnel lowers to the temperatures that they run at, that the whole structure contracts and then re-expands again, and there are these great big mechanical levers that allow it to do that expansion and contraction. And so when I talk about that and present the formula in my class, I've taken a picture of it and we can have a nice discussion about that. And the last question they asked is, where else will we disseminate this information? So we have some plans.
Our local school district, certainly. We're going to present to our high school and hopefully middle school and other schools that may want it. State and regional professional conferences. We have plans right now for a science and a math conference at the state and regional level. And community groups. We've actually been in our, when we went out to seek sponsors, we had a lot of interest from community groups to present when we return, so we'll be doing that. Our time here has inspired us and opened our eyes to new ways to excite our students about science, technology, engineering, and mathematics. We encourage all middle and high school STEM teachers to take advantage of the educational resources NASA has to offer and consider applying to one of their professional development programs. We had a great time. Thank you very much, NASA and RTI.
You rock.
Thank you.